This is section 13.1, Vectors in the Plane. This is the first section of all of Calc 3. Hopefully you've watched some kind of introduction video before this that explains what the plan is and what the point of all of these videos is. These videos just go into the details of the sections that we cover and don't talk about how the class is organized or anything. But the one thing that will always be on the screen for these videos is up here is all the different data types that we'll be using in the class. If you can understand all these different kinds of objects by the time the semester is over, then you'll be good. I'll put a little arrow next to the ones that we're working on. So chapter 13, we learn all about vectors. And as we go through the class, I'll point at different ones of these and we'll get different, we'll talk about different things. Also, every section has the objectives for the section up at the top. So you can kind of like check them off in your mind as you go, like what are we doing and why are we doing it? And these are the same objectives that are here at the top of the notes for the section. I just try to go through them as quickly and efficiently as I can. So let's go. So this is 13.1, vectors. The whole class is all about vectors. Vectors are the main way that we deal with 2 dimensions and 3 dimensions, the way that we were only dealing with 1 dimension in Calc 1 and Calc 2. All the most awesome facts about calculus at the very end of this class, they're Green's theorem, Stokes' theorem, and the divergence theorem. They require us to really have a good handle on vectors in order to have any idea what they say. That's just where we start. So the goals for the day are to understand usefulness of vectors. We'll try to get some real-life examples of why vectors would appear in your life. Then we'll explain some basic vector concepts. We're going to use a lot of different types of vocabulary and notation when we do this. And you don't get to pick your favorite, you have to be expert in all of them. Then we'll do some vector operations and do the basic properties. And then at the end, we'll get to do some application problems that have a little bit to do with physics. This is not a physics class, but calculus was built to be the language that physics is spoken in. So it's kind of connected to physics here. So let's see what happens. So first thing is, what is a vector? The best picture we have for a vector is that it's a line segment, but it's got a direction chosen. So it's a directed line segment, also known as like an arrow. The arrow describes both the direction that it's pointing and a magnitude. Magnitude meaning size. Or maybe its length. So where a line segment basically just like, it certainly has some kind of orientation and a length. A vector points in a specific direction, and also the vector knows how long it is. So here's a vector. Here's a different vector. They're pointing in the same direction, but they have different size, so that's a different vector. Here's the same vector. The first and third vectors here are the same vector, even though they're in different places. If you're pointing in the same direction and you have the same size, then you're the same vector. This is not the same vector. It's the same size, but it's pointing in the opposite direction. So these are all vectors. We'll need some nice way to write about them, but yeah, a vector has a direction and a size. The opposite of a vector, the object that you've used most often in math classes before this one, is a scalar. A scalar is a number. Like 6 or 10. 10 doesn't have a direction. It's kind of like it's just got a size. Yeah. So a vector is an arrow, a scalar is a number. Right now, those seem obviously very different from each other, but as we go through the semester, as you can tell by the fact that I've taken up some of the screen by just like, what are the data types? It actually will get confusing which objects are numbers and which objects are these vectors. And keeping those separate from each other is really important. Okay, let's get a picture of some vectors. So we'll call this vector PQ. This is one way to refer to a vector. You give a start point and an end point. We will almost never refer to them this way. This is just how we introduce them. So we'll say start at the point 2, minus 3, and end at the point minus 1, 1. The vector PQ is the vector that starts at P and goes to Q and has this direction. Sorry about the... Yeah. So this is a vector. If you pick up the coordinate plane and remove it from the picture, you have the same vector. We think of this vector as being just its direction and its magnitude. It doesn't, so to be clear, it's the same vector if you put it in a different place. So like, let's say you draw this vector where you move everything up by 1. This is the same vector. This is completely different from how we think about line segments. We would think about two line segments in different places as being different line segments, but two vectors that have the same direction and the same size, that's the only information there is in a vector. So if they have the same direction and the same size, they're the same vector. Okay, sure. You can call it equivalent vectors if you're worried about it, but I'm always going to refer to these as just the same vector. So this example says sketch 2 more vectors that are equivalent to PQ. I've already drawn one. It's the same vector. If you just go somewhere else and also go left 3 and up 1, 2, 3, 4. It should be a straight line, but I'm drawing on this drawing tablet, so we do our best. These vectors are all the same vector. They're all equivalent to each other. On to the next page. So the thing that we have in common for our vectors that are all the equivalent vector are that y2 minus y1 was always 4, and x2 minus x1 was always 3. Ooh, wait, it was minus 3, because we went to the left 3 and up 4 every time. What you notice is that this measurement, the change in y and the change in x, seem to be the actual measurements that define what the vector is. So what we do is we take the difference of the x's, like the end point minus the start point. Notice that you do, that's the way you should do it, the end point minus the start point. You take that difference of the x's and put it in like slot 1 of this thing that kind of looks like an ordered pair, except it has angle brackets. And you take the change in y and you put it in the second slot. This is called the component form of a vector. There's lots of different ways to write vectors, and this is just one representation of a vector. So our vector, we wrote it as like, here's the start point and here's the end point. But in component form, you could write that vector as angle bracket minus 3, comma 4. Notice that it's not a point. This is not an ordered pair. It's not the point minus 3, 4. It's by putting the angle brackets there, we're explaining that, yeah, we're talking about like a whole class of arrows that all point the same direction. They point left 3 and up 4. This contains both what direction they point and how long the vector should be. It's called component form. Okay, find the component form for the vector with initial point minus 4, 5. 1, 2, 3, 5. So here's minus 4, 5. And terminal point minus 1, 1. So here's our vector. To write it in component form, we just decide how far it goes in the x direction and put that in the first slot, and how far it goes in the vertical direction and put that in the second slot. This one goes right 3, so we get plus 3, and down 4, so we get minus 4. Notice that the order matters here. You have to do the end point minus the start point to get the correct values here. So here's our vector in component form. Then it says graph the vector between the 2 points and graph the component form vector. This wheel, when this comes up, is just me changing colors. What that means is there's like a standard way to graph the vector 3 minus 4, and that is to start at the origin and go over 3 down 4. So this vector is the standard way to graph the vector 3 minus 4. But it's important for you to understand that this vector is also the vector 3 minus 4. It's just drawn in a different place. It's kind of like a long time ago when you did geometry, you would say that you had two, if the two triangles had the, if you had two triangles and they had the same sides and the same angles, they were basically the same triangle. That was called congruent in geometry. For vectors, if it's basically the same vector, because it's the same size and the same direction, then you say they're equivalent, and we refer to them as being the same vector, just in different places. Okay, the question asks, how is this vector related to the vector on the previous graph? Ooh, this is a really good point, that the singular, we're using the singular here, that this blue vector and this green vector, they're the same vector. On the previous page, we had a vector that looked kind of similar, but it was pointing in the opposite direction. So how is this vector related? This vector, oh dear, the whole point here is to use angle brackets. 3 minus 4 is pointing in the opposite direction, but it has the same magnitude. The arrow on this page is the same size as the arrow on the previous page, but it's pointing in the opposite direction. Okay. The magnitude, we keep talking about this, like what's the size of the vector. There's another word for the magnitude. It's called the norm. If you ever have anybody taking the norm of anything, they're trying to describe the object with a single number. So I'm trying to think of an example outside of math. I don't have one. The sociology word norm is not the same. But this works outside of math class. So anytime that, if you have a physics object and somebody is trying to take the norm of it, they're trying to measure it with a single measurement. That's its norm or its magnitude. This is its length or its size. If you want to find the magnitude of a vector, well, I have good news for you. Anytime you have anything that's not pointing directly side to side or directly up and down, your kind of instinct should be that the best way to do any math on an object that's at an angle is to get a right triangle on the picture. And this instinct, it should be pretty ingrained at this point, especially if you take a physics 1 class. This is the main skill in physics 1, is you have some object that's not going directly to the right or directly down. So you just draw a right triangle on the picture and then everything's fine. I know I'm simplifying a whole discipline, but this is a critical skill. When you see a geometry diagram that doesn't have a right triangle on it, you should feel like you have the power to just put the right triangle there. That side length is not -4. That doesn't really make sense. But to find the length of this vector, you just use the Pythagorean theorem. You write magnitude this way, with vertical bars around it. So you draw the vector and put vertical bars around it. The vertical bars find the magnitude of an object. You've used this before. If I put vertical bars around 6, you would say, oh, that's the absolute value of 6. Or if I put vertical bars around -6, you'd say, oh, that's the absolute value of -6. And in both cases, you get 6, which means that these numbers have the same size. It's just that one of them is positive and one of them is negative. So these absolute value bars are being used all over math to determine the size of an object. If there's ever absolute value bars around an object, that's its magnitude. Here, the absolute value, you don't say absolute value when it's a vector though. The magnitude of this vector, well, we're looking at the vector 3 minus 4. And you just use the Pythagorean theorem. So you square all the components, add them up, and take the square root. In this case, we get the square root of 9 plus 16, so you get 5. So the magnitude of this vector is 5. And this is no like new magical object or new magical calculation you're doing. Instead, this is just basic geometry that you've done forever. As long as you feel comfortable putting a right triangle on a picture when there isn't one there. Okay, so the other part of a vector, I told you earlier that a vector only has two pieces of information. It has its magnitude and its direction. We know how to find the magnitude of a vector. You just use the distance formula, the Pythagorean theorem. Do I get to like put the formula for the magnitude anywhere? Oh, it was on the previous page and I missed it. Okay. Yes, here it is. So the magnitude of a vector v, it's sometimes written with just absolute value bars. Sometimes you'll see it with double absolute value bars, and these are just to make sure that you understand that we're not taking the absolute value of a number. So you'll see the double bars when someone is trying to be like extra clear, but single bars are also going to be used all the time. Anyway, the magnitude of a vector, if you know its two components, is, well, the first component tells you how far over it goes, and the second component tells you how far up and down it goes. So it's just square root of v1 squared plus v2 squared because of the Pythagorean theorem. So this is the magnitude of a vector. Now we want to work toward a formula for the direction of a vector also, so that you can figure out like all the pieces of a vector just from its component form. Okay, if we were in an in-person class, I would get to have you like talk to each other, but that's not the situation. So the direction, what we'll do is we'll try to find an angle. Yeah, so there's going to be a lot of trigonometry in here, and that's in this class. That's just because this class has to do with more than one dimension. There's always a lot of trigonometry anytime you're not in one dimension. So we're looking at the vector -3, 4, which goes left 3 and up 4, kind of like this. Make sure that you resist the urge to label it as a point with an ordered pair. Instead, you should use these angle brackets to show that you're talking about a vector. The direction is going to be this angle. If we can describe the vector with its components, we also want to be able to describe the vector with its length and its direction. We already have a formula for its length. So how do we find this direction? Well, same deal, it's just trigonometry. So we're going to say that for -3, 4, we're looking for some angle where, let's get the right triangle in here. Is that the one we want? I think so, yeah. This one is going to the left by 3. This is going up by 4. And the magnitude of the vector is 5. So whatever this theta is, we know that cosine theta is -3/5, and sine theta is 4/5. From this information, you'll be able to get an angle theta. Sometimes people try to make a formula for the direction using arctan, and that doesn't really work very well because arctan only gives you answers in a range like between -π/2 and π/2. This angle needs to be out here. So as long as you look at both the cosine and the sine, then you'll be in good shape. Here, what's going to be our best way to write this? If I take the arcsine of 4/5, arcsine of 4/5 is down here. Wait, arcsine of 4/5. 4/5 is positive. So arcsine of 4/5 will just go up this far. So I don't want that. Instead, arc cosine of -3/5 that contains the information that we're over here in the second quadrant. So I'll say that my direction is arc cosine of -3/5. So the direction of a vector, it ends up that we don't actually have a very good formula for the direction of a vector. You're either going to use arc cosine of v1 over the magnitude, or you're going to use the arc sine of v2 over the magnitude. And we're going to cross off this sentence because this is the reason that you can't really get a single formula. So whichever one of these gives you the right answer based on how arc cosine and arc sine work, that's the one you use. So the direction is kind of like a little bit slippery to get our hands on. I can't give you one formula for it. The way these notes were written, it was intended for me to give you an arctangent formula, but the formula doesn't work. That's what this sentence is for. So I'm not giving you the bad formula. Instead, I'll tell you that it's complicated and you have to check. If you run into things that you don't remember, that you're like not an expert in from trigonometry, you need to take the effort to like find the 10-minute video that's like a refresher on that object. So if I told you, oh yeah, arc sine of 4/5 is up here and arc cosine of -3/5 will give us the correct angle, and you're like, sure man, I don't know, what are you talking about? You need to find a video that is like refresher of inverse trig functions and just watch it. And then after you watch it, if you're like, yeah, I still like, I'm going to need some expert help just to remember how this works, that's what our class periods are going to be for. So class periods are office hours. You need to ask me that kind of question. Nobody has a 100% perfect foundation of all of the calculus that comes before this. It's going to be really hard for me to convince you of this in an online class. Even in an in-person class, usually people come up with the idea that everyone around them is super competent and that it's like a bad idea to ask any questions, where in fact, that's not the case. Everybody has some stuff missing from previous classes, and it's your job to be filling those in as we go. So ask questions. Other people around you will be really happy that you asked the question. I'll also be happy. Okay, let's find an angle here. So this is a vector in component form that's 2 minus 1. So it goes right 2 and down 1. The angle, well, just like from trigonometry, there will be two ways to write it. You can either go all the way around like this, or you'll be able to say it as a negative angle. I probably want to say something that comes up with a negative angle here. Okay, what's going to be the best way to do this? Well, first I need to find this hypotenuse, like the magnitude of the vector. The magnitude of a vector is no big deal. You use the distance formula or the Pythagorean theorem. And I get the square root of 5 here. So whatever this angle is, it has a cosine of 2 over square root of 5 and a sine of -1 over square root of 5, this angle. It's so sketchy to draw it there, this angle, I guess. Okay, if I do the arc cosine of 2 over square root of 5, I'll get a positive angle in the first quadrant. I don't want that. If I do the arc sine of -1 over square root of 5, I'll get something in the fourth quadrant, which is what I want. So the angle is the arc sine of -1 over square root of 5. That's our direction. So you've got formulas for the magnitude and the direction. The magnitude is a number, it's a scalar, and the direction is an angle. Okay, let's do some stuff with vectors. Say you have two vectors. You can do arithmetic with them. This is called abstract algebra, where we learn how to do algebra to objects that are not numbers. So here we're going to add and subtract vectors and see what else we can do with vectors. Okay, to add two vectors, say you want to find u plus v. One thing I should note to you is that often in writing, in typed materials, the name of a vector will be bold to try to tell you that it's a vector. And the name of a scalar, of just a number, will not be bold. And that's to try to just give you some context clues about which things are vectors and which things are scalars. When it's unclear, like in this case, what kinds of objects these are, what you can do on paper is put little arrows on top of them. And usually people don't draw the bottom part of the arrow, so they just draw like half arrows like this over the letters. And that's our way to say, hey, this is a vector. It's got a little arrow decoration on its head. I don't know, you give it a little hat. And that shows that we're talking about a vector here. It's not required to do that. It's just kind of polite to the person reading it if you're being more clear. It's kind of like capitalizing a proper noun. It's just everybody would still be able to figure out what you were talking about if you didn't capitalize a proper noun, but it just like helps, it makes it easier to read. Okay, so how do you add two vectors? Well, you just add the components. So you add the x components and put the result in the x component, and you add the y components and put them in the y component. Similarly, that's how subtraction works. This is called doing the operation component-wise. So you zoom in on the components, and you just do the operation to both components. I want to tell you that it's important how this is defined, because we don't add the magnitudes, and we don't add the angles. The addition of two vectors, the sum of two vectors, it's defined to be the sum or difference based on the component form. The magnitude of a vector could change in a totally different way if you add it to another vector. When I write an equation like this that has an equal sign, but I'm writing it as a definition of what I mean by the left side, I'll often put colon equals. Colon equals is like, it means equals, but it's like stronger than that. It says, this is the definition of the thing on the left side. So when I say u plus v as two vectors, it means, like, this is, if you looked it up in the like encyclopedia of what math is, u plus v for two vectors would be this. It's not like they just happen to be equal. Okay, so what else can we do? We can take the negation of a vector. The negation of a vector flips it around. And the way you find minus u is you do it component-wise. You take the opposite of its two components. If it was going to the right, now it's going to the left. If it was going up, now it's going down. Similarly, you can multiply a vector by a scalar, a number, and this is where the word scalar comes from. And I hope you're paying attention. This is because these words, they come back over and over, and a lot of people make it through all of physics and calculus not realizing why things are called a scalar, like why we renamed number to scalar. This is why we renamed it. It's because if you multiply a vector by a scalar, by a number, it scales it up. So if you multiply a vector by 2, it keeps the direction and just goes, it's twice as big. So here's like u and 2u. If you multiplied it by minus 2, it would make it twice as large and flip it in the other direction. And the way you do that is if you want to multiply a vector by the scalar c, then you go into the components and multiply each component by c. So these are the vector operations. You can add, subtract, negate, and multiply by scalars. What's missing from here is how to multiply two vectors together. We'll figure out a couple different ways to do that later in the chapter. But addition, subtraction, negation, and multiplying by a scalar, like scaling them up or scaling them down, those all just work component-wise. Okay, here's some vectors. I think you know this, but you can pause and take a break, or like rewind, or run me in slow motion, or run me at double speed, like anytime you want. That's one of the main like benefits of having these as videos, is you don't have to sit here and stare at me. So every time we finish a page, you can be like, okay, I'm pausing and I'll be back later. Whatever. Okay, so given two vectors, let's graph these following things. So along with the original vectors, where are we putting all these? Okay, whatever. Half v is scaling the vector v down by a half. So half v, you go into the components and multiply them both by a half. It was 4, 1. Now it's 2, 1/2. So what does that look like? Here's 4, 1. And then 2, 1/2 is the same direction, but the magnitude is cut in half because it's been scaled. It's been multiplied by a scalar. Okay, minus u. Minus u is you go into u and you negate all of its components. What does that look like? Well, you had a vector that went right 2 and up 3. The new vector minus u goes left 2 and down 3. So it's the same vector, but flipped around in the opposite direction. Okay, What about 2u? 2u goes into the vector u and doubles all of its components. So instead of 2, 3, you'll have 4, 6. What does that look like? Well, you had, whoops, 2, 3 is more like this. You had 2, 3. Now you'll be twice as long, but in the same direction. So here's u and 2u. Okay, u plus v is a little bit more tricky to see. It's easy to calculate it. U plus v is you just go in and you add 2 plus 4 is 6, and 3 plus 1 is 4. So you'll go over 6 and up 4. The question is, what does that have to do with u and v geometrically? So here's u plus v. Well, here's the trick. If you draw u was 2, 3. And then you start at the end of u, and you put v at the end of u. So from here, you go over 4 and up 1. Then you can see how u and v combine to form u plus v. So if you add two vectors together, you can add the vectors geometrically by going this way. One thing you should notice is that since addition is commutative, you can do it in either order. You could also do v plus u, and you end up in the same place. So u plus v happens to be the same thing as v plus u. And that's just because we defined it component-wise. This is a complicated looking picture now that it's over, but yeah, if you put two vectors like head to tail, then the resulting vector is the sum of the two vectors. U minus v, okay. Well, u minus v, what was u? U was 2, 3, and v was 4, 1. U minus v is 2 minus 4 and 3 minus 1. So how do we get this on the picture? Okay, this goes, u minus v goes left 2 and up 2. So here's u minus v. To do this, start by going in the direction u. So you go over 2, up 3. And then v would head off in this direction, over 4, up 1. So u plus v is out over here. But u minus v instead takes v and flips it around backwards. Go left 4 and down 1. So here's u minus v. You end up over here, and that means you can draw the resultant vector u minus v this way. So we're just trying to get some intuition of vectors. I'm sorry if you've had a whole bunch of physics and you're already an expert in vectors, but maybe you got some perspectives about vocabulary by doing this. Yeah, we would normally do this in class, but we do not have a class to do that in right now. Okay, here's a theorem. Hopefully you know what the word theorem means. Most people don't, though. The word theorem means surprising math fact. So a theorem isn't a definition. Like, it's not like the way that I defined a word. It's like after I set up the definitions to be something reasonable, sometimes surprising facts fall out. Like the Pythagorean theorem is like, well, it didn't feel guaranteed that a squared plus b squared would equal c squared. It just like happens to be that way all the time. So anytime we have a fact that like just comes out of our definitions, if we argue logically, we call it a theorem. If the fact is not surprising, if it's an obvious fact, then we wouldn't call it a theorem. We would call it like a proposition or a lemma or something like that. A theorem is supposed to be like, aha, this is crazy. Like, whoa. There's different levels though. This one is not that crazy. What this says, so this says, why would this make sense? What is each side saying? This says that the magnitude, and magnitude you can say you can say the magnitude as norm or as length or size. So the magnitude of c times v on the left side, and then equals means is, and then the right side is the absolute value of c times the magnitude of v. What does this tell you? It tells you that if you scale a vector, that scales its magnitude. So if you take a vector and you multiply it by -4, it becomes 4 times as large. If you take a vector and you multiply it by 6, it becomes 6 times as large. So that's what this theorem says. It basically says, okay, scaling actually works as scaling the way that we say it does. And this theorem is the reason that it's okay to call numbers scalars. Okay, how can we prove this with a picture? I don't really want to prove it with a picture. The picture would be you draw v and you draw cv and like it's c times as long. I'm more convinced by the algebraic argument. So whenever I give you a surprising math fact, I'll give you a proof of it. And this is just the culture of mathematics, is that like I'm not interested in giving you facts and telling you to believe and memorize facts. I'm interested in showing you that these facts just like are true and they like can't be taken away from us. It's not like people in other countries or on other planets or in other galaxies will have different facts. Like these are just the facts. If we meet aliens, they'll have the same scalar theorem. So here's our proof. Our proof is, most of the proofs in this class are actually, you take the thing on the left side. Notice the double bars here, just to emphasize that the left side is a vector and this c is a scalar. So if you have like an absolute value and a magnitude in the same equation, you might use double bars to talk about the magnitude, just to like distinguish between them. Anyway, the way proofs work in this class usually is you take the thing on the left side and you write down what they mean. So what is CV? Well, CV is you go into the vector and you multiply its two components by c. And then what does the magnitude mean? Well, the magnitude of a vector is, you use the Pythagorean theorem or the distance formula, however you're thinking about it, which is you square the components, add them together, and take the square root. Then there's one algebra trick here, which is both of these terms have a c squared in them. So you can factor out the c squared. When you factor out the c squared, you have v1 squared plus v2 squared. What happens with this c squared? Well, square root of c squared is c. I'd like to point out that that is a common misconception. So we'll fix this in a second. So I'm putting an exclamation point here to remind us to come back. But let's finish what happens here. Then the square root of v1 squared plus v2 squared, well, that's the magnitude of the vector v. So we showed that the magnitude of cv is c times the magnitude of v. But that's not what we were trying to show. There's actually something here with an absolute value. So what? Why did that happen? Here's your warning. It's possible that you've run into this before, but the square root of c squared is not c. Yeah, why is that? Well, imagine trying a negative number. If you take the square root of -3 squared, well, -3 squared is 9, and the square root of 9 is 3. So we took the square root of -3 squared, and we didn't get -3. Instead, actually what happens is that the square root of c squared is the absolute value of c. So that's where these absolute value bars come from, is that the square root of c squared is actually absolute value of c, and that finishes the proof, that the thing on the left of our theorem is equal to the thing on the right of our theorem. And it just happens because of how the definitions worked out. and because of this weird number effect. So that's our first theorem. The theorems at the end of the class are significantly more complicated and way more awesome, so sorry if that one's boring. Okay, let's look at this vector. We've got the vector 3 minus 4. It will turn out that we will be very interested later in the class in vectors that have length 1. These will be called unit vectors. This terminology, using unit as an adjective, is all over math. I think probably the place you're most likely to have seen it is you've heard of the unit circle. Like, what do you mean the unit circle? Well, there's lots of circles. We call it the unit circle if it's the circle with radius 1. So it's like if the size of your object is 1, then you call it a unit object. Here, a unit vector is a vector of length 1. Well, this doesn't have length 1. This vector has length 5. So how do we get it? It's like too big. It's like 5 times as big as it's supposed to be. How do we scale it down to have a length of 1? Well, you scale it down by its magnitude. So the unit vector that's in the same direction as 3 minus 4 would be multiply the whole vector by 1/5. And to do that, you scale down both components. Side note is that this vector points at a point that's on the unit circle, because the unit circle is all the points that are 1 away from the origin. So anyway, this is a unit vector. It's a vector with length 1. So here's the formula in general. A unit vector is you take your original vector, you divide by its magnitude. The end result is a vector of length 1. Often we will use the letter U to refer to unit vectors. Not always, but like often. So to make a vector have the same direction but have a length of 1 is to normalize the vector. So you'll hear me use that word. It'll like slip out sometimes because it's like a standard word. It's not super important. It's not as important as all the other stuff in this section. But if someone asks you to normalize an object, that means to get it down to like a standard size, and that's size 1. So to normalize this vector, we say, okay, first I'll find its magnitude. 2 squared is 4, 5 squared is 25. So I get the square root of 29. This vector has length square root of 29, but I'm looking for a unit vector. That's what normalize means. So I'll divide by its magnitude. To multiply or divide a vector by a scalar, you use it on all of the components. So this whole vector will be scaled down by the square root of 29. Okay, there's a couple of important standard unit vectors. The standard unit vectors, or the coordinate unit vectors, are the unit vectors that point toward the positive axes. So I is the unit vector that points in the x direction, the positive x direction. So on your axes, I points toward positive x, and j points toward positive y. They're unit vectors, so they have length 1. So this one's 1, 0, and this one's 0, 1. Later, we're going to get vectors that are in 3 dimensions, and then we'll have a third standard unit vector called k, which is pointing like up in the z direction, out of the xy plane. But that's for later. Okay, so this is another way to represent vectors, another way to write them, and it turns out to be really useful sometimes. Basically, instead of saying it in component form, over 3, down 4, you could say, okay, go 3 copies of I and minus 4 copies of j. You can use the little arrow instead of the dot over I and j to show that you're talking about like the unit vector I and the unit vector j. This seems like a really weird way to write it, but it will turn out to be really helpful in some cases. It's just another representation of vectors. The picture of why this works is like kind of funny, I think, because to draw the vector 3 minus 4, you just go over 3 and down 4. And if you're thinking of it as 3i minus 4j, that's because you say, okay, here's 1i, 2i, 3i. So here's 3i minus j, 3i minus 2j, 3i minus 3j. Okay, 3i minus 4j. But that's just another way to write it, to write the same vector. This word linear combination, if you take a linear algebra class, this is really important. Linear combination just means you have some i's and some j's added together. Yeah, this isn't a linear algebra class, so I won't spend too much time on linear combinations. Okay, so let's go to the last page of this section. So consider this vector. This is a kind of vector that we'll work with a lot. They're called direction vectors. The vector cosine theta, sine theta, you saw all throughout trigonometry, all of their terminal points lie on the unit circle. So the vector cosine theta, sine theta picks an angle and goes over and up just enough to go 1 unit out in that direction on the unit circle. Let me get out my notes because I do not remember what I was going for here. Okay, all unit vectors, that's what we're going for here. Any unit vector lands on the unit circle, and so if you look up its angle, you can write it as cosine theta, sine theta. And that means that any vector you could break up by figuring out which direction it goes, which would be cosine theta, sine theta, and its magnitude to scale it up to the right size. This is called the magnitude direction form of a vector. This is probably the least important, but it's still important enough to bring up. So we had component form. Did we have a name for the form with i's and j's? I don't have a special name for that. This ij form, and then we've got the magnitude direction form. Okay, so write the vector with magnitude 4 and angle pi over 3. So we're going this way, length 4, and magnitude pi over 3. How do we get that vector? Well, if you know the magnitude and the angle, then you should just use the magnitude direction form. So this is v is 4 cosine pi over 3 sine pi over 3. Then we can find cosine pi over 3 and sine pi over 3. Cosine pi over 3 is a half. Sine pi over 3 is square root of 3 over 2. Once I get this scaled up by 4, I'll have my final answer. 4 halves, that's 2. And 4 square root of 3 over 2s is 2 root 3. So here's the vector that goes in the direction pi over 3 and with magnitude 4, written in component form. Okay, this example says, have you ever played the snow tube game? I have no idea what that is. What? Okay, apparently it's awesome. If a tube is pulled at 45 degrees with 250 pounds of force and minus 60 degrees with 100 pounds of force, what is the resultant force vector? Okay, I don't know what's going on with the tube. I'm sorry. But let's say you've got some object. I guess I'll guess that it's probably an inner tube with a person sitting on it, maybe? Maybe that's what makes it fun. And you say you're pulling it this direction with 250 pounds of force. And then also at minus, so here's 45 degrees. And also someone is pulling this way with 100 pounds of force. Then which way is the tube being pulled? The answer is, if you apply 2 forces to the same object, you can write the forces as a vector. So write vectors for the forces. And if you apply 2 forces to the same object, you can add the vectors together, and you just get another vector, and that's the total force. If you've taken a whole bunch of physics, you're like, yes, obviously. But I don't know, the perspective from the math perspective on this is really? That's crazy. why would it be addition? Like, why would the world work that way? And the fact is that it just does. So, like, I can't prove how the world works, but I can just tell you, and that's called physics. I mean, I can just tell you. I can convince you by showing you experiments. That's called physics. If I can just prove it by writing stuff down, that's called math. Okay, so let's write the vectors down and add them. So the first vector, we have its magnitude and its direction. And the second vector, we have its magnitude and its direction. And I can just add these together. That's the resultant force vector. So let's get this written down. The first vector is going to be 250 times root 2 over 2, and 250 times root 2 over 2, plus the second vector will be 100 times a half, and 100 times minus root 3 over 2. These simplify a lot, so this is 125, this is 125, this is 50, this is 50. And then when you add the vectors together, you add them component-wise. So in the x component, I'll have 125 root 2 plus 50. And in the y component, I'll have 125 root 2 minus 50 root 3. These vectors added together like geometrically, it would be pick up the vector down here, move it over here, and then go this way would be the sum of the two vectors. Algebraically, the sum of the two vectors is you just add them component-wise, and that's our answer. Okay, that's it for, wait, is that it? Yeah, that's it for 13.1. Hopefully we got the objectives hit. Let's look at the objectives. We got a couple real-life examples, basically force, and that's, I think, it. I guess that's one real-life example, is that vectors are the best way to represent forces, because they have a magnitude and a direction. Basic vector concepts using relevant vocabulary, variance notations. Yeah, there were a whole bunch of different notations. There was the component form, there's the ij form, and there's the magnitude direction form. Those are all the different representations. The different vocabulary, we've got magnitude, norm, size, length. Those are all the same thing. There's scalar versus vector. Yeah. Perform vector operations. The main thing to notice about the vector operations is that we did not multiply a vector times a vector. We multiplied a scalar times a vector, and we added vectors together, but we didn't multiply a vector times a vector yet. So don't do it yet. There's a couple ways to do it, and none of them are the easiest way. The basic properties, well, we saw a theorem and we proved it, and then we applied it to a force application. So that's 13.1. Do some homework. The only way to really succeed in these classes is to practice the homework and then do the homework that's required and then upload the homework and get feedback on it so that you learn it by practice. So do it and then get on to 13.2. Cool.